flipped classroom video for Maths AS Unit 1, locating stationary points and curve sketching. So here's a summary of the classification of stationary points that you've seen previously, and we see that the gradient for all of them at the stationary point has to be 0, but if we look at the behaviour of the gradient for a maximum, it's going from positive through 0 to negative. That means it's decreasing, and that means the second derivative is negative. For a minimum, it is going from negative to 0 to positive, and so that means the gradient is increasing, which means the gradient of the gradient is positive and greater than 0. For a stationary point of inflection, we can see that for this one, the gradient is positive, then 0, and then positive, and that means it's first decreasing, hits 0, and then is increasing. So in order to identify a stationary point of inflection, we need to know that the second derivative is 0 at the point, but also that it changes sign. And remember that this could be the other way up as well. So if the stationary point of inflection were the other way up, then the gradient would be negative, then 0, then negative, and the change of sign would be from plus to minus for the gradient of the gradient, or the second derivative. So let's have a look at an example. Investigate y equals 2x cubed minus 3x squared minus 12x plus 5 for stationary points. Draw a sketch of this curve, clearly indicating the stationary points and the point where the curve crosses the axis. In the video Finding Stationary Points, we found that this curve has stationary points at minus 112 and 2, minus 15. We know that a cubic with a positive x cubed term looks like one of these diagrams. So we either have the classic sort of up, down and back up again, or the one with a sort of flat bit in the middle. Because we have two stationary points, it must be the left-hand diagram, so we can put that in. We also know that the minus 112 must be to the left, as it were, and the 2 minus 15 must be to the right. We also need to put the axes in, so if we can work out where it crosses the y-axis, that will be helpful, and that means putting x is 0 into the equation for the curve, and that gives us the point 0, 5. So that point is there, and we can then put the y-axis in. We can also then put the x-axis in because it must be below that point, so between that point we've just added and the 2 minus 15, so there we are, it goes across there, and it all makes sense. This method works for curves that we know the shape of, but we don't always know what the shape will be, and also it's not enough for exams, so we need to calculate the nature of the stationary points. To do this, from having got to this point, the first step is to find the second derivative, d2y by dx squared, and so we start with dy by dx and we do the derivative of that, which gives us d2y by dx squared is 12x minus 6. Second step is to use the second derivative to find the nature of the stationary points. So that means we have to put the x value into that expression for the second derivative, which for the point minus 112, x equals minus 1, and so we have 12 times minus 1, take away 6. We don't actually even have to work that out. If we can look at it and see obviously it's going to be less than 0 because both bits of it are negative, then we can just state that it's less than 0, and therefore we have a maximum. So if we sketch our curve as we go along, then that tells us that that point must be minus 112. We can then put the x value of 2 into the second derivative. This time we can see 12 2s are 24, take away 6, still going to be positive, so that's greater than 0, and therefore it's a minimum. You may prefer, by the way, to work out the final value of the second derivative to then establish it's less than or greater than or even equal to 0. That's absolutely fine, of course. So we can now put that point on the curve as well, and then we can proceed writing down, if we were doing an exam, what we're doing, and we will arrive at that sketch. And then if we look at the sketch done on GeoGebra, we can see that we've done a reasonably good job there. Okay, let's have a look at another example. Draw a sketch of the function f of x equals x cubed minus 6x squared plus 12x minus 7, clearly indicating the stationary point / points and the points where the curve crosses the axes. So, step 1, find the stationary points. dy by dx is 3x squared minus 12x plus 12, that's coming straight from f of x, and dy by dx is 0 when that expression is 0. So we can divide through by 3. We can then do our little table to work out factorising. Probably with this one you'd spot it straight away, but we have that minus 2 and minus 2 multiply to 4 and add to minus 4. So that gives us our x minus 2 times x minus 2, which is x minus 2 squared. And that being equal to 0 tells us that x minus 2 is 0, and therefore x is 2. If we put x equals 2 back into the function to find the y value, then we get that expression there, 2 cubed, take away 6 times 2 squared, plus 12 times 2, take away 7, which gives us 1. And so therefore, this curve only has one stationary point, which is the point 2, 1. Step 2, find the second derivative and use it to find the nature of the stationary points. So we have d2y by dx squared equals 6x minus 12. That's by differentiating dy by dx. And so the second derivative when x equals 2 is 6 times 2, take away the 12, which is 0. So it's looking like we might have a point of inflection, but we need to check whether the second derivative changes sign at this point. So if we think about d2y by dx squared when x is less than 2, well, when x is less than 2, 6x minus 12 will be less than 0. Similarly, when x is greater than 2, 6x minus 12 will be greater than 0. So we have our change of sign for d2y by dx squared, and we can conclude that we have a point of inflection, a stationary point of inflection in fact, at 2, 1. And there's a little sketch of it, not a great sketch because it doesn't show that that's a stationary point of inflection at 2, 1. You'd probably get away with it as long as you state that that's what you intend the point to be. Step 3, find the points on the axis or axes for this curve. So first of all, we can put x equals 0 into the function, and that gives us y is minus 7, so that means the curve goes through 0, minus 7, and we can show that by showing the point and drawing in the y-axis. Now for the x-axis, that's a bit more difficult because we need to find values, or a value. In fact, you can see from the sketch that it's just going to be a value, where f of x is equal to 0. But if you look at the numbers there, we've got a 1, a 6, a 12 and a 7, and 6 and 7 is 13, and 1 and 12 is 13. So f of 1 is a good try, and in fact we can see that that gives us 1 cubed minus 6 times 1 squared plus 12 times 1 minus 7, which is indeed 0, and so we know that the point on the x-axis is going to be 1, 0, and we can put that point in and show the axis there. So that's an actual plot of it from GeoGebra, and we can see that our sketch wasn't too bad.